Gosh, are they? Ah, there we are. That's our sign to start. Welcome to is this the last one of these of this semester? This is the last one. This is the last Astro seminar. We have Keith Hawkins from the University of Texas, Austin. He's going to talk about galactic archaeology. In addition to being a professor at UT Austin, he is the SDSS-5 spokesperson. So if you have questions about SDSS-5, by all means ask him.
If I don't know the answer, I'll just ask him. Okay, welcome everyone. I'm Keith Hawkins. I am an associate professor of astronomy at UT, but I actually was a postdoc at Columbia University in New York not that long ago, and then moved to Texas in 2018. So it's good to be back in the city. I was a Simons Fellow right around the time CCA was actually just starting up. I work on galactic structure, galactic dynamics, galactic chemical abundances, stellar abundances specifically, and the intersection of that with machine learning. I do a lot of work with both ground-based observatories like Sloan, like McDonald Observatory in West Texas, but I also work very heavily with Gaia. And so if you're interested in using Gaia for whatever science you're doing, I'm also happy to chat about Gaia as well. I work in an area called Galactic Archaeology. I should probably say okay to this.
Yeah, there's some.
Should not showing up on my machine. Oh, that's
fascinating.
I can see it. It's on the, oh, yes. Perfect. Okay. Yeah, so I work in an area called Galactic Archaeology, and I'll describe a little bit about what that is through the questions that interest me in studying the universe, and in particular our galaxy. So when I was starting in graduate school, I became very interested in how do galaxies in general form, evolve, and assemble themselves over cosmic time, and how do they form the various components that they're made from. I also was interested in studying how galaxies assemble themselves over cosmic time, and how galaxies are structured, how galaxies like the Milky Way are structured. And if, as a galactic archaeologist, the goal of galactic archaeology is to answer those questions about galaxies in general, using the Milky Way as a laboratory for doing that type of study. Obviously, the Milky Way is just one galactic system in the universe, but it is the system that we know the most about. It's the one where we can actually see and get a lot of information about individual stars. And so it's one of the best places to really do this type of analysis, to really study galaxy formation and evolution, but with the Milky Way context. I've put the years there because those are roughly the years that I got interested in these particular questions. And as I moved through my career, I got interested in more questions like extreme velocity stars and how elements are made, specifically elements that are key for life in the universe, how multiplicity in terms of stars affects a star's life, but also how it affects the properties of the stars that we see. And then I even had a mid-career crisis, which was started here. I don't even know if I'm mid-career yet. Maybe I am.
I don't think you are yet.
Maybe not. I'm in the mid-career stage of associate professor, so maybe.
Okay.
So I had a crisis when I was here. David Hogg and David Spergel began arguing about whether the Milky Way was even a spiral galaxy. Like, this is classic, right? And I took away from that debate. Maybe we should go and figure out if it really is a spiral and try to find the spirals. Again, find the spirals, and I'll talk a little bit about that in this talk. David Hogg is very contrarian, and it's great. And so one of the things that I realized is that I have too many questions, which is why I became a professor and why I have a group of students that help me answer these questions. In particular, that leads me to the goal of this talk. Since I have so many questions and my research program kind of touches on areas not only with galactic and stellar astronomy, but also with planetary astronomy and all kinds of other areas of astrophysics, my warning here is that the goal of this talk is to give you some breadth of this type of science that my group is interested in. In particular, I'm looking to see if there are collaboration points here in the audience. And so I'm not going to go into a high level of detail about any specific project, but I'll kind of give you a more broader overview of some of the topics that my group is interested in case you might be interested in those topics as well. My research group, the way I like to think about my research group is I work on stars as tracers of galaxies like the Milky Way. This is galactic archaeology. I work on stars as stars, so stellar structure, stellar evolution, That's much more like nuclear physics related and the physics related to stellar structure. I'm interested in first stars, and probably the strongest connection to this department might be near field cosmology, which is using very low mass, very old stars as traces of the early universe. And I'm also interested in stars as tracers of planetary systems. So know thy star, know thy planet. And so this is my research group, and my core area of expertise is really in stellar chemodynamics, using low to high resolution stellar spectroscopy to understand and try to answer some of these big questions. So I have a core research area and a set of ancillary science areas that I work on. But most of the work, pretty much almost all of the work that I do is really either in the Milky Way or in the stars and groups and galaxies surrounding the Milky Way. And so I wanted to give you a little bit of sense of what the Milky Way is, just in case you're not used to thinking about it. So this is an artist's impression of the Milky Way galaxy, our galactic home. We're a barred spiral galaxy, an SBB. So the bar is the thing here in the middle. And then we have beautiful spiral arms, or what we think are spiral arms, in the kind of extending from the bar region. The sun is about 2/3 of the way out of the galaxy at about 8.3 kiloparsecs. That's about 28,000 light years. On an orbit that's about 230 million years. The last time the sun was in this rough location was right around the time the dinosaurs were walking around here. We live in a galaxy that has five major structural components to it. The galactic thin disk is where the sun lives, the thick disk, the galactic bulge, and the halo. And I'll describe each of these, especially because I know this department, you guys don't have probably that many people working on the Milky Way itself. So I'm going to orient you. So the thin disk of the galaxy is a very thin component, and I will actually use my favorite meal of the day to describe this in breakfast food analogies. So the thin disk of our galaxy is like a French crepe. It's very thin in terms of aspect ratio. It's rotationally supported, so all of the stars are going around. Its velocity dispersion of the stars are low, so most of the stars are going around in fairly circular orbits. It's kinematically cold. They're fairly young stars, so 0 to 8 gigayears age. The spiral arms likely live inside of the thin disk of the galaxy. It's fairly metal rich, so metallicities of -0.1. This metallicity diagnostic basically is the bracket notation for this means that it's the log of the number of iron atoms in the star divided by the number of hydrogen atoms minus that of the sun. So an iron abundance in this notation is 0, means that it has the same iron content as the sun. -1 means it's 1/10. -2 means it's 1/100th, and so forth. There is a negative radial metallicity gradient, which will become important later on. So the inner galaxy is metal rich and the outer galaxy is metal poor in the thin disk. And there are azimuthal structures in the metallicity gradient that is likely related to dynamics, but the spiral arm likely also potentially related to the spiral arms. And so I'll talk a little bit about some of the work that we're doing on that. The thick disk of our galaxy, so you have your flat crepe. You're surrounded by a fat American pancake. That's the thick disk of our galaxy. It was discovered in 1983 by Gilmore and Reed. If you just basically look upwards out of the galactic plane and you count the number of stars you see, you expect the number of stars in an exponential disk to just fall off exponentially as you go up in the galaxy. That's this line here. So this is a paper from '83 where they showed that indeed the number density of stars does fall off as you move up in the galactic, as you go up in the galactic plane, but at some scale height, it actually falls off much slower than expected. And they attributed this to an extra thicker disk. You have a component, a thin disk here and a thicker disk here, and when you combine those two, you get the full profile you see. So that's the thick disk of the galaxy. That's where it was discovered. It was actually discovered in other galaxies first, in Yoshi 1982, for example, and then Gilmore and Reed found it in '83. It's rotationally supported, kinematically hotter, so that just means the stars are going around with much more eccentric orbits. It's older than the thin disk and likely formed as the belief is the thick disk formed first. The thin disk probably formed out of what was going to be the thick disk. And it's moderate metallicity. So the metallicities are much lower than in the thin disk. And there's little to no metallicity gradient in the thick disk, and this is likely because the gas that formed the thick disk was very turbulent, very well mixed, and so the inner parts of the galaxy saw the same chemistry as the outer galaxy because of that well mixed gas. And then finally, we've got the stellar halo. So I had a hard time for a long time finding a breakfast analogy for this one. The best one I could come up with is you have your flat prep surrounded by a fat American pancake. You batter it up and you deep fry it in the very American way. And that deep fried batter on the outside is the stellar halo surrounding the galaxy. The halo is pressure supported, so all the stars are kind of going in random orbits, fairly eccentric. It's the oldest component of the galaxy. It's therefore the most metal poor. There are probably multiple populations, an inner and outer halo, or at least an in situ and accreted part of the halo. And the halo is now thought to be built largely by one LMC size thing that fell in about 8 to 10 gig years ago, called Gaia Enceladus sausage, depending on who you talk to.
No chance of changing that name.
Sorry?
No chance of changing that name.
I think it's embedded in the literature
Damn
now. I will tell you, yeah, at some point, I will tell you the story of how.
Although strangely, you did not connect it to your breakfast analogy.
I did not, no, I should have. The Gaia Enceladus I tried to call when I was a graduate student, Atlantis, after the lost city of Atlantis.
Oh, there you go.
My PhD advisors told us that we couldn't publish that paper, so we didn't. And then years later, Gaia, it was first called Gaia Sausage.
Oh, I see.
That's the story. Gaia Sausage is, in my opinion, a terrible name, but it was named after the discoverer's daughter, whom he calls the silly sausage.
Oh.
That's where it comes from.
Okay.
And then finally, you've got your thin French crepe surrounded by a fat American pancake. You deep fried it up, you battered it and deep fried it, and now you plop a big ball of butter in the middle. That big ball of butter is the bulge. Pressure supported, it's as old as the halo, but it's much more metal rich. It's very fast star formation, lots of successive generation of stars. And so the bulge is kind of where you have a lot of old, but surprisingly metal rich stars. There are also some very metal poor stars there, and it's likely that the oldest stars in the galaxy, those that were formed, a few billion years or like even less, maybe a billion years after the universe formed, probably sank to the galactic center and are sitting in the bulge somewhere. So there's a very high value in finding metal poor, very old bulge stars. And so Maddie Lucy, which was a former PhD student of mine, did a very beautiful set of works trying to understand the galactic bulge, in particular the metal poor component of the galactic bulge. And Maddie is an NSF postdoctoral fellow at Penn, but comes regularly to CCA, so she's in town a lot. So this is our galaxy. This is my laboratory. This is the best picture, so to speak, that we have of our galaxy. The bulge there in the center, the thin disk surrounding it with all the beautiful dust lanes, the thick disk, and the halo on the outskirts. And there is a debate still about these particular components, although less so now. When I started, I started my career at Ohio University. My undergrad professors basically told me that stars in the Milky Way were solved problems, and there were only 2 big problems left in astronomy: cosmology, which I guess this department is as well, and planetary astrophysics. And then I went to Europe and realized that wasn't true. That there's a lot of really interesting things going on in stellar and galactic astronomy. And so, but if you go into the literature, there are quite a lot of debates about each one of these components individually. Do they exist? Are they real? And so forth. I will quickly skip over this. This is kind of for folks, for the graduate students in the room that may not be as familiar with galaxy formation theory, but essentially the way we think galaxies form, there were 2 primary theories behind galaxy formation, 2 classical theories behind galaxy formation. There was Egan, Lindenbell, and Sandage in 1968, which basically says that you basically take a big gas cloud and you let it fragment and collapse and form stars that way. And then that forms, of course, elliptical galaxies. Then if you give it some angular momentum, the process of collapse through conservation of angular momentum will spin the thing up into a disk, and that's how you get disk galaxies out. This did not explain all of the relevant data at the time, including and specifically the location and distribution of globular clusters that were being discovered in that day. And so a second theory came out in the 1970s from Cyril and Zinn, which is that galaxies form by actually accreting and merging on top of each other. Basically, it's this hierarchical galaxy formation is essentially galactic cannibalism. Galaxies go, big galaxies go and eat little galaxies and form bigger things. And so that's how we now believe galaxies form, is some combination there of these 2 primary theories. I'm going to skip this slide and just say that simulations show that it's probably some mixture. You could form proto-galaxies from monolithic collapse. Those proto-galaxies merge and then create larger structures. If you want to learn, though, about this process, the problem is you can't watch it happen, right? This happens on giga-year timescales. But what you can do is you can take snapshots of it happening either in the local, in the universe, the local universe. But in addition to that, you can actually, since all of this has happened to and within the Milky Way, you can use the Milky Way as a laboratory for studying these particular questions. And the reason why this works is because every star in the galaxy is a fossil. Most importantly, it's a fossil because the chemical composition of the surface of the star, generally speaking, doesn't change over the course of its life. That's not entirely true. There's some elements where it does change. But because of that, you can use the chemical fingerprint of a star now to figure out what the universe was doing chemically billions of years ago when it was born, because it's locked that information in. Similar to tree cores here on Earth, right? You can cut down a tree, although I don't necessarily recommend doing that. You can cut down trees and look at the tree rings and learn about how Earth has evolved based on tree rings. That's kind of what we're doing, but we're doing it on a galactic scale with stars as tracers. And the reason why I got into this area is because right around the time I was going to graduate school, there were all of these beautiful, large-scale surveys that were starting up of the Milky Way, or either ongoing. So there, at the time, there was the RAVE survey, radial velocity experiment. It was not collecting spectra for hundreds of stars, but thousands or millions of stars. Gaia, of course, was launched. SDSS-5, SDSS-4 and 5 were happening. And so we were getting into a phase where there was just so much data to really understand the Milky Way. For the graduate students in the room, I will say one thing that really helped me throughout my career is that I tied a lot of my work to Gaia. And Gaia basically came around as I went through my career. So the first, Gaia was launched in the fall of my first year of graduate school. Gaia's first data release was when I became a postdoc here at Columbia. And when I was here in New York, we actually were hacking on the Gaia data. I got my first faculty position when Gaia launched its second data release, and I got tenure on the third data release. I don't think I can get full on the fourth, but given the way they're pushing it, I might be able to get full before that. So I literally tied my entire career steps to the Gaia mission. And so when I developed my group at UT Austin, I actually decided to do a divide and conquer approach. I was very interested and excited about all of the components of the Milky Way, but I just couldn't study all of them myself and with a whole amount of detail. So I sent each one of my grad students to a particular region of the Milky Way. They got really good in that particular region of the Milky Way, and then they taught me about it, which is great. So Maddie, who's now a fellow, an NSF fellow at Penn, studied the bulge. I had a couple of students, current students, Dionysus and Zoe, who were studying the galactic halo. And I had a large number of students also studying the disk. Catherine Manea, whom I want to point out. These are the two people actually local in the New York region. So Maddie is an NSF fellow at Penn and comes into CCA a lot. And Catherine just started as an NSF fellow at Columbia University, just up the road here as well. So these two students are former students of mine, are doing really great work studying galactic and stellar astronomy, and they are actually pretty local to this particular region. So the rest of the talk really is going to be some of the exciting research and results that we have in this particular area. I wanted to start with the tools. So I'm really excited about answering the question of how does the Milky Way form and assemble itself over cosmic time? That's like the overarching question that I have. But to answer that question, we actually need tools. And some of the tools that we use, one of the primary tools that we use is chemical tagging and cartography. So I'll talk a little bit about what those two tools are. If you want to understand where a human being comes, what do? Let's say you want to know where your ancestors are from. What would you do?
DNA.
You take a DNA
In
test.
courthouses.
You'd use some form of DNA, right? You can take a 23andMe test. I have mixed feelings about that. Does the government really need my DNA? We'll see. But what we can do is we can do exactly that, but we can do that with stars. So the DNA is the chemical composition of the star. Remember how I said earlier, since the chemistry of the star doesn't change significantly over the course of its life, that means that you can use the DNA, the chemistry of the star, as its DNA. And it tells you about where it was formed. And so chemical tagging, which is what I'll start out with, is one of the primary tools that a galactic archaeologist has to figure out where a star was born. Chemical cartography is another one. Chemical map making is a very important tool that allows us to figure out how the galaxy is structured, because different structural components have different chemical signatures. And so chemical tagging and chemical cartography are the probably two biggest tools. And I'll start with tagging because it's something that has been a debate in the field for a long time. So to describe chemical tagging, I liked to use this analogy. So this is chemical tagging from none other than M&Ms. You can see I'm on a food kick, even though we just had really great food. So I'm actually kind of full. So imagine that the Milky Way and every galaxy can be reduced to just simply a bag of M&Ms. Every galaxy is a bag of M&Ms. The Milky Way, each Milky Way, each of these M&M bags is a protogalaxy. You can think of it as a galaxy. And the stars within those galaxies are different colored M&Ms. So this bag of stars, so to speak, are only blue stars. This bag of stars is only green, and so forth. And in this analogy, the Milky Way basically has, in its process of forming, has done nothing more than gobble up a bunch of little protogalaxies to form itself and assemble itself. And so the Milky Way today is not this, but in this analogy, it's just a mixed bag of M&Ms of different colors. And the question is, can we actually go back in time and figure out which M&M came from which bag? Because if we can do that, then what we can do is figure out the Milky Way has actually merged with, to create the Milky Way, we needed 5 protogalaxies. And those 5 protogalaxies merged to create what we see now as the Milky Way. So the Milky Way's assembly history can be done if you can figure out which stars, which M&Ms, came from which galaxies, which bags, so to speak. And so the question is, can you do this? And the answer, according to chemical tagging, is yes. You can look at the color, its chemistry, and figure out that it came from one system or another. Now, for chemical tagging to work, the goal of chemical tagging is to determine the birth location of an individual star based on its chemical fingerprint alone. This came out in Freeman and Glenn Hawthorne in 2002. And there's 2 primary requirements of chemical tagging. One, every star that is born in the same region have to have the same chemistry, right? That's saying that every M&M in the bag has to have the same color, basically. Otherwise, you can't do chemical tagging. That's requirement. Second is that stars that are born in different regions of the galaxy or in different galaxies have to be chemically different from each other. If a star was born in the bulge and born in the outer galaxy and it's chemically the same, then even if I can figure out their chemistry, the tags are useless and meaningless in some sense. Okay, so every star born in a different region has to be chemically different. This first one is asking the question, are stars born together chemically homogeneous? And the second one is whether or not the chemical doppelganger rate is low. Okay. If you look at the literature, there are 2 flavors to this. There's strong chemical tagging and weak chemical tagging. I don't really have time to talk about it, but I just wanted to make the distinction. Strong just means that you can tell exactly where a star was born based on this chemical fingerprint alone. And weak says you can't tell exactly where it was born, but you can tell roughly what region it was, global region it was born inside of. And so chemical tagging is an important question. It's an important tool in the Galactic Archaeologist toolbox. And millions and millions of dollars, Australian dollars specifically, have been spent on surveys devoted to chemical tagging, like Gaia. And so answering this question, does chemical tagging actually work, is actually quite important, and we've already invested a lot of money in it. And so it's basically like asking the question, are 2 stars, wide binaries, actually, because wide binaries are likely born together, are these 2 stars chemically homogeneous or not? The answer could be yes or no. If it's yes, it's assumed to be yes, not just for chemical tagging, but also characterizing exotic stars like M dwarfs, for example. So the planet folks usually try to find stars around M dwarfs because it's easy. We don't really know how to characterize M dwarfs very well, although Hogg has done some work on this, many people have done work on this. And one way you can do it is by finding an M dwarf in a binary pair with an FGK star that's easier, and then assume that the FGK star and the M dwarf have exactly the same chemistry. That assumption requires that stars born together are chemically identical. So this is assumed to be yes for lots of things. So if the answer is yes, we're good. If the answer is no, we're kind of in trouble. So in pops a beautiful study from Sung-Myung Oh in 2017, done actually in this at CCA. where Sim Young basically found a set of co-moving pairs of stars that were likely born together. John Brewer then had a chemical abundance catalog. They did a cross match and found that there was a pair of stars that have not only they were born together, they're co-moving, but also they had detailed chemistry. And they found, interestingly, that if you look at the chemical abundance patterns, this is the X/H ratio for different elements of one star in blue and one star in red, that they're chemically quite different. So these are two stars that are born together. So the red and the blue line should be on top of each other. And yet within errors, they're wildly, wildly different. That's not good for chemical tagging. That is actually a bad thing for chemical tagging because it says that stars that are born together may actually be chemically quite different. And then your chemical tag doesn't work. And there's also this particular question has been studied. There's a lot of literature on this, and I've put dots on each side because I just wanted to mention that there's been a lot of literature on this. But if you just go and ask, does chemical tagging in the literature? If you just ask that simple question, you get some answers. Like this is a paper from La Casamaquela in 2021 saying chemical tagging is absolutely not going to work just because of the chemical degeneracies between. About 5 or 6 months later, another paper comes out by Spina saying it's absolutely going to work. It's like the literature is a complete mess in terms of whether chemical tagging will or won't work. And so what we did was we decided when I arrived at Texas, let's go back to the basics. Let's test those original assumptions of chemical tagging. Let's test whether stars born together are indeed chemically homogeneous, and let's test whether stars are chemically different if they're born in different regions of the galaxy. And so to do this, we took Sim Young's and later Karim El-Badri's wide binary catalog. We then actually went to the Javier or the 2.7 meter Schall spectrograph on the 2.7 meter at McDonald Observatory, and this was great because I got to train my students on how to do observational astronomy. And these are us taking spectra of wide binaries, and we actually determined the detailed chemical patterns of those wide binaries. And if the chemistry is alike between the two stars, chemical tagging should work. And if it's not alike between the two stars, chemical tagging won't work. A pretty simple problem and question and an experiment. Does chemical tagging work? Is the main question. The kind of specific question is, are stars that are born together in wide binaries chemically homogeneous or not? The answer could be either they are chemically homogeneous, good for chemical tagging, or they're not chemically homogeneous, bad for chemical tagging.
Can you just say, like, from the point of view of the theory of star formation,
Should they be?
And yeah, like,
yeah,
like would it not be extremely strange for them to have very different?
It would be extremely strange for them.
Like that would, okay.
So the theory says that when you have these giant molecular clouds that are forming, those clouds are often fairly turbulent, and then things quiet down enough as things cool and condense, things quiet down enough for a star to be formed. But because of the turbulent nature of the star forming cloud, you'd expect all of those chemicals to get mixed up, and the chemical mixing actually should homogenize the gas cloud.
Okay.
There are
when
situations.
It cools, it doesn't. There's no differentiation that might happen.
Not between two stars. That will happen on planetary scales.
Yeah. Okay.
When specific ice lines are met, but that won't happen on the stellar scales. So two stars that are born from the same GMC should have almost identical chemistry. In theory.
So if the answer is no, you just have another line of research to.
Yeah.
Yeah.
There are theories for why it doesn't work, which is like, let's per se, this is going a little bit off topic a little bit, but let's per se you have a GMC here and an AGB star. The AGB winds are not very strong and can affect this part of the GMC, but not this other part over here.
I see.
That's a contrived scenario where theory would suggest they would be different.
Got it.
But there's other theories and we'll talk about some.
All right.
Sorry, what's the difference between this one and the red and blue abundances you showed like 1 or 2 slides ago?
Yeah, so that was a single pair of stars where you found that the two different lines meant the chemistry of those two stars in that single pair were different. What we're doing here is we're going to do this, but on a much larger scale. So instead of 1 pair, we're going to do this for 25, and in the end, we end up doing for 130 pairs. So
So it's common for stars in binary systems to have widely different temperatures.
Yes.
So, I mean, due to that, is it possible, like, are we probing the metallicity of these stars? Like, is there any selection effect because of the temperature?
No. And the reason for that is because we selected stars at the same temperature. We specifically selected pairs of stars that have similar temperatures for both stars to account for that. And that's actually shown in this slide here. If you're a stellar spectroscopist, you'll see this immediately, but each one of these colors is a different set of pairs of stars. These are the high resolution stellar spectra that we collected from McDonald. The solid line is one star and the dotted line is the other. And I challenge you to find the difference, especially on the top, on these three. That's how you know they're the same temperature. They're the same temperature, they're the same metallicity. In fact, they're the same entire abundance patterns. And in fact, this kind of belays the point a little bit. This is the kind of summary plot from that particular paper. This is my 2020 paper, where we show that the abundance, if you just take the abundance difference between two pairs of stars and the dispersion of that, this is the total error in reds in black circles that with which we think we can measure a particular element. This is the measurement that we see, the difference that we see in wide binaries in red and in orange in random pairs of stars. And so you can see within uncertainties, because the black is usually at the same or less than the red, we actually do not, with an error, measure a difference. In fact, our errors are probably a bit overestimated. Our errors are probably somewhere down here in most elements. But we can see wild differences between random pairs of stars. And this, in fact, suggests that if you try to ask the question, are wide binary pairs of stars identical or fraternal chemically, they often always tend to be identical. There were about 15 to 20% of the cases, though, where they were not, where they actually were fraternal, they were different. This 10 to 25, 10% of these actually turned out to be not chemically homogeneous at all, similar to the Kronos and Krios pair. So what we argued in this paper was that Kronos and Krios result, which showed that the wide binaries were wildly different, it does happen, but it's only about 10% of the cases that it happens if you go to much larger samples. This particular question I liked asking because I myself am a twin. This is me and my twin brother, Kevin. We're fraternal, but the universe tends to make identical twins. We actually extended this work to a significantly larger sample of stars, separating stars by larger and larger distances. So this is Tyler Nelson's work. He was a PhD student with me now. He's a lecturer at the University of Southern Maine. Tyler then we extended this sample to a much wider set of stars, going out to 3D pair separations well over a parsec. This is the separation of the pair on the x-axis and on the y-axis. You see the difference in the chemical composition, specifically metallicity. And you see that generally speaking, the stars in wide binary pairs are chemically homogeneous, even out to very large separations, although it does break down after a few parsecs. And that's because after a few parsecs, you're more likely to get pairs of stars that are actually not related at all, but rather dynamical captures of each other. And what about those 10% of stars that were not identical? Why can that be? There's a couple of theories. One is atomic diffusion. So the heavy elements will tend to sink in an atmosphere of a star. Light elements will tend to rise. It could be mixing episodes. So stars undergo mixing episodes that change their chemistry as they evolve, as they bring up heavier elements that have been formed in fusion. It could be radiative levitation. So you actually can, through very hot stars, the radiation pressure on the atmosphere is enough to push up some of the heavy elements, causing the heavy elements to levitate. That can change the abundances. And you can also get planet engulfment. So engulfment of material from somewhere else that wasn't around, or that's different than what the star is. You can, yeah.
How could something like levitation work if they're both the same temperature? Wouldn't that happen in the same way for both stars?
Yeah, that's why that's next.
Ah.
You were getting to my next point, which is that we can rule out mixing episodes and radiative levitation and atomic diffusion, actually. We can rule out mixing episodes because the stars haven't evolved. We chose stars that didn't evolve yet to have mixing episodes. Radiative levitation can't work because the stars are not hot enough, and both stars will achieve the same amount of levitation since it's temperature-based. And you can almost rule out an atomic diffusion because, again, we chose stars that are comparable temperatures and surface gravities. So stars that are at the similar thing. So the last thing that's left is planet engulfment. And it turns out the Kronos and Krios paper from 1970 argues that indeed it is like, they think that it's likely some type of planetary engulfment that causes this. You can kind of tell that it's planet engulfment because one of the telltale signatures of that is if you plot the abundance difference that you see as a function of the condensation temperature of the element, then you find that there's a strong correlation where the elements that are volatile are not at all enhanced, and the elements that are enhanced are the refractories. What's important about refractory elements is that refractory elements go into planet cores. They make the planet. The irons, the nickels, the chromiums, the cobalts, that's what makes the planet core. Whereas these light elements like carbon and oxygen make the planetary atmosphere. And if you basically eat a bunch of rocks without really any atmosphere, you're not going to enhance the things that go into the atmosphere. You'll only enhance the things that go into the planet core. And that's the argument behind why it's planet engulfed. We were pretty excited about this when there was a Nature paper that came out earlier this year, which showed exactly the same result, that at least 1 in a dozen planets, about 8%, show evidence of planetary ingestion, and what we found was 10%. So we actually, this was using a slightly different sample than us, but we actually had this result, years before, a couple of years before this result actually came.
How much planet do you need?
Couple of Earth masses.
Okay.
So they do some detailed studies, both in this paper and in this, I don't have it with me, but in the Simming O's paper, they also do a couple of detailed studies of how much rocky material you put in. It's usually a couple of Earth masses.
Okay.
Of rocky material, so
Yeah.
Okay, so the nice thing is that means that planets basically, when you think about that, 8% of their stars or more engulf their planet. So when I got right around the time I got tenure, I was doing galactic science, and then I was like, let me do something just crazy because I have tenure now, so why not? And so I started a project where we went into the Gaia XP spectra and tried to find a different kind of star, white dwarf stars, that were eating their planets. White dwarf stars have almost no spectral lines. They have very few spectral lines. They only have broad Balmer lines usually. And some white dwarfs have extra lines, metal lines in them, likely from the accretion of rocky material. And what's cool about white dwarfs is that you can actually know which lines are from the planet and which lines are from the star because they're so distinct. And so this gives you one of the few ways of actually determining what planets are made of, because you actually can measure for the first time the interior pieces of the planet as it's getting singed onto the white dwarf star. And so we started a project to try and find polluted white dwarfs in the Gaia XP spectra from the XP Exploration Workshop in Cambridge. I think you were there. I don't know who else was there from this group. I talked to many white dwarf people before, especially ADT. Do you think this is possible? They said no, because the spectra are just too low resolution. They're RF 70. And so the way you find, generally speaking, is a polluted white dwarf is you have to go, white dwarfs are very faint. So you have to do a spectroscopic survey of a bunch of really faint things and then see if they have metal lines or not. That's not the easiest thing to do. Sloan has done this for a long time and other surveys have as well. But Gaia is one of the largest survey of white dwarfs in terms of their spectra, even though the spectra are really low resolution. Gaia does have a lot of more than a million, several million, in fact, R of 11,000 spectra, but no white dwarfs show up in there because they're too faint. So that's unfortunate. But they do have 220 million XP spectra, and there's about 100,000 white dwarfs in that sample, but the resolution is like 70. Just to give you a sense of what that means visually, so this is visually what a white dwarf spectrum looks like, and this is visually what a polluted white dwarf spectrum looks like. So top panels, these two panels are actual polluted white dwarfs. You can see the strong metal lines if you just compare this, which just your hydrogen Balmer lines, to this, which is lots and lots of metal lines. The task we had was to go from, this is the typical spectral resolution that you have when people do white dwarf abundances or polluted white dwarfs. This is the quality we actually have. That's very good. And so we actually took all the white dwarfs in XP. I'm going to skip over some of this. We did manifold learning on it. So we basically ran a UMAP algorithm, it's like TSNE. And what it does is this manifold basically selects spectra that looks similar puts them in the same region of this 2D space. Spectra that look different go on a different region of the 2D space. And the argument was that polluted white dwarf spectra, because they have extra metal lines, they're all going to be grouped in some region that looks different than your normal white dwarf that have non-metal lines. And in fact, that's exactly what we found. So if you just look at the white dwarfs, if you take the region where there are known polluted white dwarfs, that's these red things here, there was a kind of a cliff in the UMAP space where there were solely polluted white dwarfs. And when we actually followed these up, we got beautiful spectra from HET, and indeed, with a 95% hit rate, we now have discovered hundreds of new polluted white dwarfs. We've increased the sample of polluted white dwarfs by about an order of magnitude than anyone else has, just from looking at the Gaia XP spectra. And we've already confirmed that 95, with a sample of only about 55, we now have 55 examples of which 95% of them are polluted from high resolution spectral photo.
And what fraction of relevant white dwarfs do show signs of pollution?
Of order 20%.
20%.
Order. That's the problem with that is it's not a volume limited sample. But
What's the time scale for this material to disappear into the?
very fast. So white dwarfs are very small and dense. So their convective time or their settling timescales are very, very short. So to see this material means that it's probably actively accreting. And by short, I mean like a few to 10 million years short.
But it is the story. I'm hearing your skepticism because I also feel it. Like there's a lot of stars with these abundance anomalies, and like, are they all really accreting like asteroids?
Right now, as we
Right
speak.
now.
Yeah, exactly.
It's a little weird.
It is a little weird. So one thing we're doing now with
Because the
this.
sun isn't accreting asteroids right now very fast. I mean, it is.
It is,
accreting
I was gonna say it is,
asteroids,
but just not.
not very fast.
So one thing we're trying to do now with this is actually we're doing two things. We want to look at, now that we have such a large sample of polluted white dwarfs, we can ask statistical questions at the population level about what is the rate as a function of galactic position. But we're also now going to be measuring elemental abundances of the polluted white dwarfs to ask how is the chemistry, the internal chemistry of a planet changing as the dynamics of the white dwarf change? As you move to say thickness versus thinness, does the planet chemical composition change? So that's what Malia Gao's thesis will be on, and that's what we're working on now. So all of that came from like a shot in the dark at a 10-year project at the Gaia XP. So and then there were lots of press releases on this as well, because people like when planets get eaten like this. Okay, so that was a diversion, but I do want to just go back to this chemical tagging question. So we talked about, chemical tagging being, needing to require that stars born together are chemically homogeneous. In 90% of the cases, they are chemically homogeneous, so at least that's satisfied. In 10% of the cases, they aren't, like the planet engulfment. The stars that are born in other regions of the galaxy, the question is, are those stars, if stars are born in different regions, are they chemically unique? You need that to be true for chemical tagging to work. I'm going to skip over this and just say they actually likely are, because the chemical doppelganger rate is low. If you want to know more information, please check out this great paper from Catherine Manea, who's now here, and I'm going to leave it just here just to let you know that it's here so that you all can find her and talk to her since she's in the New York area. I'm going to skip that section and entirely and just say that they largely are. I'll also mention that we've done some really great work with chemical tagging now that we know that those two criteria are satisfied. We, for example, have looked at young stellar streams in the galactic disk and have tried to chemically tag where those are coming from. I've written a paper on this, and Catherine Manea has written a great paper on this. We have used it to find the origins of the fastest moving stars in the galaxy, so hypervelocity stars, where those things are coming from. We were able to show, so hypervelocity stars are stars that are unbound to they're moving so fast they're unbound to the Milky Way. They're light, they were thought to be formed through something called the Hills mechanism, where you take a binary system that's orbiting the black hole, you get a triple body gravitational encounter where one star gets captured by the black hole and the other one gets the rest of the orbital.
The black hole at the center of the Milky Way.
Yes.
Yeah.
The other one gets shot out at very high speed because it gets the remaining orbital energies of what was once a binary star in a binary star system. Our detailed chemical fingerprint has showed that if you look at the detailed chemistry of the hypervelocity stars, they don't look anything like the galactic center. So the Hills mechanism can't be the only thing that's producing. And so chemical tagging was a way for, and that was actually my first NSF. I should mention, I put NSF in the corner there because that was my first NSF RU project as an undergraduate student. And that was also my first NSF grant as a faculty. So it all kind of comes full circle. We've also used chemical tagging, or Maddie Lucy has used chemical tagging in the bulge to really learn how it was formed. Again, I don't have time to talk about that, but Maddie's around in the New York region, so I'd highly recommend not only hiring her, she's awesome, but highly recommend kind of finding her out and talking to her about the bulge. We've also used it in the stream of, or we've also used it in the stellar halo to study the origin of things like the orphan stream, which has an unknown origin, or it has an unknown, we don't really know what its progenitor was. I'll skip over that.
Can you not skip over that?
Yeah, I cannot skip over that. I basically have my talk in like segments so that I can skip over things. So the orphan stream is this stream of stars here. If you look in the stellar halo of the galaxy, one thing you can see already in this image are there are these beautiful streams. There's a stream here, a stream here, a stream here, and a stream here. Each one of these streams is caused by a globular cluster or some substructure that's basically being gobbled up right now by the Milky Way, and it's being shredded apart into a long stream that you can visually see. The PAL 5 stream, for example, it's hard to see here, but there's a dot in the middle there. That's the globular cluster that's being shredded apart. Sagittarius is a dwarf galaxy that's being shredded apart. G1, I think, is a globular cluster that's being shredded apart. But the orphan stream is a stream of stars that has no known progenitor. We don't see a dwarf galaxy around it. We don't see a globular cluster around it. So where is this progenitor of that stream? What is it? That's why it was referred to as the orphan stream. It had no known parent. And so one thing you can do with chemical tagging is you can ask the question, what is the chemical composition of the orphan stream? And why this is interesting is because dwarf galaxies have a very different chemical signature than globular clusters. Globular clusters show an anti-correlation specific elements, dwarf galaxies don't. So if you study the chemistry of the orphan stream and they show an anti-correlation in the same elements that globular clusters do, then clearly it must be coming from a globular cluster. If it doesn't, then it's probably coming from a dwarf galaxy. That's exactly what we did. We studied the detailed chemical fingerprint of stars in the orphan stream with apogee. This is just showing the alpha over iron as a function of metallicity for stars in the Milky Way in gray, Sagittarius, which is an example of a dwarf galaxy, and globular clusters, which are these orange points here. The different symbols are different globulars. Interestingly, notice how every globular cluster doesn't show an increasing trend with decreasing metallicity in the alpha abundance. The globular clusters are kind of these patches here. Whereas Sagittarius, which is a dwarf galaxy, shows a clear increase with decreasing metallicity at alpha. Phenomenologically, it's different. And importantly, in the magnesium aluminum plane, this is a plane in which globular clusters are known to have an anti-correlation. So all the globular cluster stars, a lot of them are way up here, whereas the dwarf galaxies are way down here. And so you can then ask the question, well, where does the orphan stream fall? If it falls up here, then it's probably from a globular cluster. That's probably its progenitor. If it falls down here, it's probably a dwarf galaxy. And so this allowed us to show that the orphan stream, the parent, must probably is a dwarf galaxy based on the chemical fingerprint of the orphan stream. And in fact, this particular rate of increase in the alpha metallicity plane allows us to figure out what the mass of that dwarf galaxy is. And we can constrain its mass to roughly the size of 4 magnets, or just a little bit smaller. And so there's now, after this work, there's been several progenitor dwarf galaxies, Grus 2, for example. Segway 1 was ruled out, but Grus 2, that is now being considered as a potential progenitor of the orphan stream based on this chemical work.
Did we take those spectra on purpose? You did? Like, okay,
How did you take the
they weren't just
It wasn't a
accidental.
mistake.
Well, or did we just happen to observe?
No, this was
those
the streams. There was like a stream.
Those streams.
Yeah.
Okay, got it. Yeah.
So this was actually this project was born in Aspen, at the Aspen Center for Physics, where we all kind of got together and we wanted to work on streams, and no one said anything about the chemistry. And I'm like, why not? The chemistry can tell you about where it was coming from. So that's where this project was at the Aspen Center for Physics, which is quite a cool place. Okay, so now that I haven't skipped over that, I am going to skip over this, which just says that we're doing some really great work with headdex. And
I like that choice.
yes. And then the final thing I'll talk about is just these azimuthal variations. That's it. I think that's all I have time for. 5 minutes?
5 or 5. Yeah, 5 minutes is great.
Okay.
We go until 3.
Okay,
So it depends on how many questions you want.
I'll go until Wait, no, I'm just kidding. So the last thing I'll talk about is expanding our work beyond chemical tagging to chemical cartography. And this is something that I'm really excited about. Because you know, kind of like the first explorers of the Earth that were going around in the seas trying to map the Earth for what it was and has taught us a lot about geography. We're now in a position with all of the big data that I mentioned earlier that we're now in that exact moment with galactic astronomy, where we are now creating beautiful large-scale maps of the galaxy and using it to understand how the galaxy is structured and how it's formed. And so this is based on 2 sets of papers, one from myself, a single author paper, and one from Zoe Hackshaw, who is a current student of mine doing some really great work on chemical structure in the galactic disk. And so when we look at our Milky Way and we ask the question, well, how did this thing evolve? Chemical patterns, chemical cartography, chemical map making is one of the key ways we can learn about how the Milky Way formed and assembled. And here's just an example. Imagine, so we're going to talk specifically about the distribution of the elements, how the distribution of elements are in the Milky Way in radius and in vertical height. So imagine you have a galaxy in which the interior part of the galaxy has the same metallicity as the sun. And as you march outward in the galaxy, the metallicity of the stars, generally doesn't change. Inner galaxy is 0, solar neighborhood is 0, outer galaxy is 0. This would imply that the metallicity gradient in the disk is 0. So as you plot metallicity as a function of radius, there is no gradient there. It's just a flat line. Astrophysically, this flat line implies that the gas that formed the Milky Way was extremely well mixed, because the gas that was in the interior mixed well with the gas in the exterior, and so the chemical composition is the same all the way throughout the Milky Way. If, however, the inner galaxy is metal rich, and as you march outward in the outer galaxy, it becomes more metal poor, then your metallicity radius diagram looks like this, and you do have a radial gradient, specifically a negative metallicity gradient. This astrophysically implies that the interior was formed really fast, and the exterior was kind of slowly forming as you go. So the interior, because it was formed fast, lots of successive generation of stars, lots of metal buildup. The exterior, not so much. If we look at the Milky Way, the other thing is that we assume, however, that there's no azimuthal variations here, that you can just azimuthally average out everything. And so we've seen metal gradients in other galaxies. It was first observed in the Milky Way and Jane's 1979 by looking at open clusters and other studies where you do see a Mayer 1976 also saw it, where you actually see in the Milky Way a negative metallicity gradient, which implies this so-called inside-out formation. The galaxy forms from the inside first, then goes to the outside. And so what we did was ask the question, with the new data that we have, we're now mapping up the galaxy in full 3D. This is the X, Y, the sun is in there, marked by the star. The galactic center is over here. The inner galaxy in real data is very strongly metal rich. The outer galaxy is very strongly metal poor. That's the negative metallicity gradient. But we're now in a position where we can ask questions about whether or not there are azimuthal variations in the disk that align with anything that tell us about how the disk might have assembled. And so what we actually do is ask this question, are there azimuthal metallicity variations in the disk or not? And the way we do that is essentially, we start with that data set I showed you earlier. We basically create a model of that. So we go, we take a just simple linear model, and if the linear model is the best model that describes the data, i.e. if there is no azimuthal structure, the difference between the data and the model should just be noise, random noise. Shouldn't be structured at all. But if you actually do this, and you take the data and subtract it from just a simple linear gradient, then you actually see significant azimuthal variations. And in fact, they align with the spiral arms. So these contours are where the spiral arms are. And so what we find is that anywhere where there's a spiral arm, the stars are slightly more metal enhanced than one would expect by the metal gradient. And in between the spiral arms, the stars are slightly more metal poor than one would expect just by a simple metal gradient. The physics of why that is something that we don't really understand yet. And I am going to delay that to question. Other than to just say, when I first saw this, I was very suspicious. I was like, holy crap, those are the spiral arms. And this started thanks to you, David. When you and David Spergel were having a debate about whether there were spiral arms or not. I wanted to see if we could chemically find them in chemical cartography, and there they are. So this got some press because we found the spiral arms of the Milky Way by accident. I don't think I was expecting to see that. We're still trying to figure out why it looks the way that it does. I will simply say that it does look, if you just look at, this is the press release on it, but if you do look at our view of the Milky Way, our artist's impression of the Milky Way, the spiral arms do seem to be slightly more metal enhanced compared to the regions between spiral arms. And we think it's probably dynamics in origin, but again, I don't really have time to talk about that. So this is ongoing work and something that I'm really excited about. So with that, I'm going to leave up a summary slide of the hodgepodge of things that I've discussed. One, we explored the tools of galactic archaeology and in particular tested the role of chemical homogeneity in white binaries for chemical tagging purposes. We've seen that in most of the cases, chemical tagging should work because stars that are born together are chemically homogeneous. We found evidence for a low doppelganger rate in the disk. I skipped over that, but that's from Catherine Manea's work. So these two results suggest chemical tagging should in principle work. You can use chemical tagging and cartography specifically to find azimuthal metallicity variations in the disk. We think this is probably due to migration of stars along the spiral arms in the disk, but we're still not really sure about that. You can ask me why later. But there's a lot of things I didn't talk about and didn't have a chance to talk about in this talk, but I do want to say the takeaway should be, I think, galactic archaeology, in particular, the tools of galactic archaeology, chemical tagging, cartography, and so forth, along with the big data sets that we currently have, make galactic archaeology, I think, a very exciting field right now. And in particular, trying to understand how the galaxies formed and assembled with all of the large data sets. So I'll stop there. You can ask me questions about anything. Happy to chat. So sorry for the hodgepodge nature. I literally changed my talk about 4 minutes, 5 minutes before because you guys said you wanted to hear about 4 minutes. So okay, yes.
Doesn't the dynamics of the stars give you a lot of information about their origin too? So chemical tagging be combined?
Yes. So one thing I put in the dynamics or in the tagging slide was that you can have dynamical tagging, which is in principle you can back orbit integrate a star and figure out where it was born. Assuming you know A, the age of the star really well, which we don't, and B, you know the potential of the Milky Way really well, which we don't. So the problem with dynamical tagging is that if it's not within, if the star is older than about 100 or so million years, dynamical tagging doesn't really work well. That said, there are spaces you can go to, like action angle space, where things still group up quite nicely. And so dynamics is a great complementary tool to chemistry. There was an argument, the reason why chemical tagging became so important in the field was because the argument was, well, we're never really going to know the potential of the Milky Way well enough to do dynamical tagging at the level we need, but chemical tagging could be what we need. And so nowadays, the argument is chemical and dynamical together give us the information we need to try and piece together the story. So I would say it is very useful, but it's a bit tricky to use.
Doesn't the time of the birth time of the star also vary greatly? I mean, like like two stars born at the same place could have different chemical signatures.
If they were born at different times.
They're born at different times.
The argument that is largely in literature is that two stars that were born in the same place at the same time likely have the same chemistry.
Right.
The question is, at the same place is not, that's a qualitative statement. To make it more quantitative, you can create a box that says a star formed within this radius of that star will be the same. That will depend upon the so-called correlation lengths of particular elements in the ISM. Those correlation lengths are based on how those elements are produced and then dispersed in the ISM. So elements that are produced in supernovae events have very large correlation lengths because the energies that go into dispersing them is very large. Whereas elements that are formed and dispersed by AGB winds, stellar winds, have much smaller correlation lengths because they don't have the energies to push out very far. So S process and neutron capture elements, which largely do come out from AGB winds, those are going to be the things that can help you distinguish on small spatial scales. So in that way, I would say same time and same place, it has some quantitative qualifiers that one needs to think about.
Gotcha.
This might be about question, but so last Friday there was a colloquium about that we see quite young stars around Sagittarius A star, which we don't expect.
We see quite young stars.
Yeah,
Ah.
in the galactic center,
yeah.
and then you said that the galactic center would be all stars which form early and they are very middle of each.
Yes.
Is there any like discrepancy in Gaia? Can Gaia see galactic center or like?
Firstly, that's a great question. I don't think there are any, in my opinion, there aren't. But I would, yes, so when I say the bulge is old and metal rich, I don't mean the region that comes from the very, very central region called the nuclear star cluster. So the nuclear star cluster is a different component, in some sense. It's embedded in the bulge, but it's primarily formed of fairly young stars, at least in the very interior. And it does, there's a corollary here to something I was talking about earlier to hypervelocity stars. So you remember how I said hypervelocity stars are likely formed by two stars going around each other. One of the stars gets captured by that supermassive black hole, the other escapes. The hypervelocity stars that we see today that likely come from the galactic center, they're all very young, very massive OB stars. Their companion are the so-called likely, the theory goes, the companion are the so-called S stars, the young OB stars that are currently orbiting the supermassive black hole that are being used to dynamically measure the black hole's mass. And so the argument right now is that the OB stars that are orbiting the central black hole, the very young ones, we expect them to come in pairs because at least out here in the solar neighborhood, OB stars likely come in pairs, by and large. In the galactic center, they don't. And the argument is, well, they did, but one of them is ejected as a hypervelocity star, and one of them is the so-called S stars. So there's no discrepancy there. It's just when I said the central part of the Milky Way, I generally mean the bulge, but inside of the bulge exists a young stellar population in the nuclear star cluster.
Center of the galaxy is a puzzle because there isn't really a predictive theory here. It's just observationally on this scale, it's old and metal rich, and on this scale, it's very, very young.
Yeah.
And there's no real theory of that at all.
Well, that varies from galaxy to galaxy.
Right.
We don't know on,
Yeah,
some
These
parsec scales
That's
of the
right.
galaxy.
it doesn't
but-
seem like a consistent property among galaxies.
Exactly.
So
And in
it's
our own
probably
Milky
just
Way,
the weather. It's probably the weather, not the.
it probably is. And in our own Milky Way, it's hard, right? One of the things that I you can kind of see if you just look at a picture of the galaxy. And I have a lot of content that I skipped, but that's on purpose. If you just look at, this is the central region of the galaxy where it's kind of bright and kind of orangey, there's a lot of dust there. And so the problem with the galactic center also is that it wasn't until very recently that you could actually get through the dust and see what's behind it. And apogee has been quite amazing as a tool. You need to go to the infrared, the near infrared to do that. And then so there's a lot that I think we're still discovering. I actually think the central region and the bulge will be a really important region to kind of study in the future because of Roman. So Roman is going to do a bulge survey, microlensing bulge survey specifically for planet searches. But there's going to be a lot that we'll learn, I think, about the bulge when Roman comes around. So I think this area that was kind of very difficult to study is its windows kind of opening.
Any other questions? Thank you again.